Acids and bases. Question type 1. Calculating pH from pH equals minus log 10 to the hydrogen ion concentration. Write an expression for the term pH. Well, that's just something you've got to learn, where pH equals minus log to the base 10 of hydrogen ion concentration. Calculate the concentration in moles per decimeter cubed of an aqueous solution of sulfuric acid. It has a pH of 0.25. Well, why would they give you a pH of 0.25? Well, clearly they want you to use this equation. So pH is 0.25 equals minus log to the base 10 of hydrogen ion concentration. So when you've got that, what you then need to do is you need to work out hydrogen ion concentration. You need to get rid of that log 10, or rather the minus log 10, but you can't use your calculator to get rid of minus log 10. So what you have to do is you have to, once you've got 0.25 equals minus log 10 to the hydrogen ion concentration, change the signs on each side. So this becomes minus 0.25 equals plus log 10 hydrogen ion concentration. So minus 0.25 equals plus log 10 hydrogen ion concentration, and you can get rid of plus log 10 hydrogen ion concentration by using shift log or inverse log or second function log. So you plug in to your calculator minus 0.25 shift log and it'll give you the hydrogen ion concentration. It should come out as 0.56. Now you've got to remember that sulfuric acid is a superacid. 1 mole of sulfuric acid makes 2 moles of H+, or you could say that 1 mole of sulfuric acid reacts with 2 moles of base. Anyway, 1 mole of sulfuric acid makes 2 moles of H+. So if you wanted to work out the concentration of sulfuric acid, then the concentration of hydrogen ion concentration, if you half it, that gives you the number of sulfuric acid. So 1 mole of sulfuric acid makes 2 moles of H+, so if you've got 0.56 moles of H+, you've got half the amount of sulfuric acid, 0.28. A student carried out a titration by adding an aqueous solution of sodium hydroxide, so that's your base, from a burette to an aqueous solution of ethanoic acid, so that's a weak acid. It's not completely dissociated into H+ ions. The end point, sometimes called the equivalence point, was reached when 22.6 cm cubed of the sodium hydroxide had been added to 25 cm cubed of 0.4 mole per decimeter cubed ethanoic acid. Right, let's do our little scavenger hunt thing. Let's work out the number of moles of this first of all, because why would they have given you concentration of ethanoic acid and volume of ethanoic acid unless they wanted you to work out moles? So concentration 0.41. So 0.41 concentration equals moles divided by 25 centimeter cubed. That needs to be in decimeter cubed. So 0.410 equals moles divided by 0.025 decimeter cubed. So to get moles, then you need to multiply 0.025 by 0.41 and you work out the number of moles of sodium hydroxide. That is going to get you that first mark. Just to go back a little bit, write an equation for the reaction between sodium hydroxide and ethanoic acid. Sodium hydroxide is that, ethanoic acid is that, and a base and an acid always make water. So what have you got left? CH3COO. The H has gone from that and the OH has gone from that to make water, HHO or H2O. So you've got CH3COO, that H has gone, the OH has gone, you've got CH3COONA. It's called sodium ethanoate. We've done this little bit. We've got the moles of ethanoic acid equals 0.0103. And so the concentration of sodium hydroxide, concentration is number of moles divided by the volume. Well, the volume is 22.6 centimeters cubed divided by 1000, 0.0226, and it comes out as 0.454 moles per decimeter cubed. It's to 3 significant figures. The reason it's to, you forget about the 0 to the left, and then you start counting the significant figures. 1, 2, 3. 3 significant figures. The reason for that is because 0.410 is to 3 significant figures. Question type 2, pH curves and indicators. Let's have a look at this one. It's starting off at about pH 3, so it's not a strong acid, but it's ending up at pH 13 or 14, so it is a strong base. That's confirmed by the fact that the pH goes up slowly here, so that's a weak acid going up slowly to pH 7, and then the pH shoots up very, very quickly then, so from pH 7 it goes up very, very quickly, right up almost to pH 14 straight away. So a weak acid and a strong base. This one is a strong acid, starts off at pH 1, it goes along and then shoots up quickly up to pH 7, and then it shoots up quickly straight up to pH 14. So the shape of that curve is a strong acid and a strong base. This one, a strong acid, because it starts off at pH 1, goes along and then shoots up quickly up to pH 7. So there's an equivalence point here where it shoots up quickly, and then it creeps up slowly from pH 7, goes up slowly, only up to about pH 11. So that's a strong acid and a weak base. This one actually is starting off as it's a strong base. It's starting off at pH 13. It's a strong base. You can see the shape of the curve. It goes along and then shoots down quickly down to pH 7, and then shoots down quickly from pH 7 right down to pH 2 or pH 1. It's actually a strong base and a strong acid. It's this shape of curve, except it's the other way around. So you're starting off, maybe in a conical flask, with your strong base, and you're adding the acid to it. Which one of those shows the curve produced by addition of ammonia? Ammonia's a weak base, so your weak base could be something like this one. C. Hydrochloric acid, strong acid. Yes, your answer is C, a strong acid and a weak base. Sodium hydroxide to 25 centimeters cubed of ethanoic acid. So that's a strong base to a weak acid. So this is a weak acid here, starting off at pH 3 and going up slowly up to pH 7, and then the pH shooting up quickly straight up to pH 13 or 14. So your answer there is A. Nitric acid, that's a strong acid to 25 centimeters cubed of potassium hydroxide. So you're adding the acid to the potassium hydroxide. This is a strong base. So you've got a strong base, and to it you're adding a strong acid, and the pH is coming down. That's answer D. Let's have a look then. We've got strong and weak acids, and you've got strong and weak bases. So if I had here acid P with base X, acid P, strong acid, with base X, strong base, you've basically got that shape of curve here with an equivalence point somewhere between 3 and right up to about 11, because that's where the pH change is happening rapidly. pH 3 up to 11, yeah, you could use methyl orange, and you could use phenolphthalein. You can use either. So this one is either. Both indicators give a precise endpoint. A. Q with base X. So Q is a weak acid with a strong base. A weak acid with a strong base. So it's this shape curve, a weak acid with a strong base, and therefore your equivalence point where it's going up quickly is somewhere between about pH 7 up to about pH 11, something like that. So somewhere between pH 7 and pH 11. pH 7 and pH 11. This one fits in between pH 7 and pH 11. The answer is phenolphthalein. Only phenolphthalein gives a precise endpoint. So your answer here is C. Q with base X. You've got a weak acid and a weak base. These ones here don't show that, but what you'd have is you'd have this shape curve coming up to here, and then you'd have this shape curve coming up to here. In other words, it would go like that up to pH 7 and then creep slowly up to about pH 10. You wouldn't get an equivalence point at all. So not having an equivalence point at all, neither indicator gives a precise endpoint. You'd have to use something like a pH meter.